All right, so alcohols can take part in both reduction and oxidation reactions. But to talk further about these, we need to understand oxidation states. So this is a review from back in Gen Chem. So there are kind of two main ways to think about how much electron density an element has. We think about this as formal charge, or we could think about this through oxidation state. And we'll take a look at methanol in both of these. So methanol, right, we have a central carbon, and then we have an OH group, right, that's bonded to it. Remember, each bond is 2 electrons. So in this case, I'm drawing them as dots like this for a particular reason, obviously. So let's go ahead and take a look at both of them, both the oxidation and the formal charge. All right, so when we're talking about formal charge, what we assume is that everything shares electrons evenly. And so this OH or this O gets 1 electron, this hydrogen gets 1 electron, this hydrogen gets 1 electron, and this hydrogen gets 1 electron, and thus this carbon gets 1 electron each from each of the 4 bonds. And so that's how its oxidation or how its formal charge is 0 right here. Because remember, the equation for formal charge is the electrons on the neutral atom. In this case, carbon has 4 electrons in its neutral state, minus the number of bonds. In this case, has 4 bonds, so 4 minus 4 is 0, and then minus the number of lone electrons. In this case, we don't have any lone electrons, so 4 minus 0 is 0, right? So in this case, this carbon has a formal charge of 0. But just because it has a formal charge of 0 in different compounds doesn't mean that it has the same electron density. So another way we can take a look at this is through oxidation state, and this one will vary much more in organic chemistry. When we're talking about oxidation state, we say that the electronegative atom gets all electrons in the bond. Right, so whereas before this OH was sharing one of its electrons, now it's going to go ahead and take both of these electrons because oxygen is more electronegative than carbon. However, in these carbon-hydrogen bonds, the carbon is going to take both electrons because carbon is more electronegative than hydrogen. And so if we think about how many electrons this carbon has, normally, or neutral carbon has 4. Here we have 6 electrons, so we get a -2 oxidation state. So we can say that the oxidation state here is -2. So let's take a look at some examples of how oxidation state can change without formal charge changing whatsoever. So we have methane here. Methanol. Formaldehyde. Acetone, and then carbon dioxide. And so if we think about the formal charge, all of this is 0 on all of these carbons, right? The formal charge here on each one of these is 0. But that doesn't mean that they have the same electron density, right? Their electron density is actually different because their oxidation states are different. And so you can do the above trick of, sharing or taking away electrons. When we go from left to right here, we say that this is oxidation, because the formal or the oxidation state of the carbon is increasing. So if you do the calculations here, you get an oxidation state of -4, right? The carbon is taking all 8 of those electrons. Here we get -2 as we saw above. Here we get 0. It's getting the electrons from the carbon-hydrogen bonds, but none from the carbon-oxygen bonds. Here we get +2. The carbon-carbon electrons are shared evenly. And then here we get +4. So we can see that CO2 is the most oxidized version. Methane is the most reduced version of carbon. And of course, going from right to left, this would then be reduction. And so we're going to take a look at a number of different reactions where we can oxidize or reduce these carbon-oxygen bonds, right? Take them into alcohols to carbonyls or vice versa.